Well, it's just about Pi Day. I did not buy this shirt. It came to me in the mail yesterday. I don't know who from. But it was great. I thought I just had to wear it today. Today is March 11th. Pi Day, minus 3 days. In fact, this year's Pi Day is a once-in-a-lifetime kind of thing. It's really a Pi moment. You heard about this Saturday, March 14th, so that's 3/14. 2015 at 9:26 a.m. and 53 seconds. Why is that a Pi moment? .1415, 2015, 9:26 a.m. and 53 seconds. Well, if you don't round, I guess if you round is 54 seconds. Have I shown you that mathematically you can do this before?
Oh, yeah. But
The
who decides it's at the morning time?
Well, that makes the most sense if you think of it as army time. By the way, there's 100,000 digits of pi. Question that you can do. Just do this. I tried it with 1,000,000, and I think it only shows you sum of the digits of 1,000,000. I guess I can try it. It takes long. Well, it doesn't really take much longer. I'm not sure this is 1,000,000 digits, but it's a lot. So I'm excited about it. Unfortunately, it's a Saturday. So we had to have our pre-Pi Day, our Pi Day celebration as a pre-Pi Day celebration. We're having a celebration for math and computer science majors. Sorry if you're not a math or computer science major, you're not officially invited because then we run out of pie. We're going to eat pie. So if you're a math or CS major, it's 9:15 to 10:15 in the Happy Lab tomorrow, which is really, I guess, we will include pi minus 0.02 moment. 3.1215926653. Okay, so pi minus 0.02 moment. I do want to try to celebrate pi minus 0.03 moment today. So we'll try to keep track of the clock here to some extent. Let's see if I keep that up there. And if I make my mathematical thing here smaller. Oh, it's not letting me make it smaller. Where's my thingy to make this smaller? I guess we can kind of do this. Okay. I guess we'll do with that. Try to tell me. Try to start waving or something if we're getting close to 9:26. Okay. I also want to make a Facebook post about it. Let's see. 3-day countdown to pi moment. I'm going to enter this at pi moment, pi minus 0.03 moment. Let's see, how many seconds are in 3 days? I think it's 259,200 seconds. T minus 259,000. What did I say? 200 seconds? Seconds and okay, so I got to enter that at 9:26:53. So let's see, we'll keep that up. We have a lot to do today. Oh boy, are we going to be able to do all this? Here's the plan for today's class. Again, like Monday, it's sort of going to be a high-level content thing. I know there's tons of details in Chapter 2 that are kind of mysterious because you're relying on the computer. The point is to see things from a high level, to see about phase planes, to see what the computer can do, to interpret the meaning of solutions. That's the main purpose. We have, a little bit with Euler's method and a little bit with analytic methods for those partially decoupled systems that you can do by hand. But for the most part, we're relying on the computer and we're just trying to interpret what we see. In Chapter 3, 4, and 5, then we get into more details on how to do things by hand. I want to introduce you to the idea of something called a nullcline today, which we're going to use the computer for again, but you can draw in some special cases fairly easily by hand, and they can help you understand phase planes. I'm going to give you a little introduction to that today. Talk about this van der Pol equation a little bit more. That was about where you have this attracting periodic solution. Within that, continue to comment about existence and uniqueness. I guess I only talked about uniqueness for autonomous systems on Monday. I also want to contrast this about what uniqueness says for non-autonomous systems. And it is a difference when you're looking at the phase plane. There is a difference. We'll once again look at the SIR model and the Lorenz attractor very quickly. Talk about something called sensitive dependence on initial conditions for the Lorenz attractor. And start chapter 3. The title of the first section of chapter 3 is Linear Systems and the Linearity Principle. So we start with nullclines here. I think I better make this smaller. Let's see, nullclines. Okay, so this, we go to the interacting species section. I now have this additional thing saying with nullclines in the picture of the phase planes. So let's look at the competing species one here. Oh, and I want to put this down so we can see the time. Put that up. So this is going to be competing species. Here are the right-hand side functions. I've entered those. Down here, I want to get the full interactivity with ND-solve and locator. And this is the picture that we saw. Let B increase and we see the solution curve. We can change the initial condition. Like I said, what I want to do now is I want to add nullclines to these pictures. What are nullclines? So we're talking about a system of two differential equations, autonomous. The right-hand side functions have no t's in them. The x nullcline is the set of points where the right-hand side function for the dx/dt equation is 0. And the y nullcline is the set of points where the right-hand side of the other equation, the dy/dt equation, equals 0. Set of points where g of xy equals 0. I hope it's pretty clear looking at this that where both of those are 0, that's where you get equilibrium points. That's what we do to find equilibrium points, is we set both of them equal to 0. But what if we set just one or the other equal to 0? We get a set of points that's probably an infinite set, usually. These are usually curves or unions of curves in the plane. And they're still going to be important. The x nullcline, where f of xy equals 0, is where dx/dt equals 0. So, this is the point, when a solution curve crosses an x nullcline, the horizontal velocity, so to speak, is 0. The solution curve is going straight up or straight down at that moment in time. The velocity vector is straight up or straight down for the solution curve. And along the y nullcline, the vertical velocity is 0, so the vector field is horizontal. And a solution curve crosses with a tangent that is horizontal. So they can help you, if you can graph them, they can help you understand what solutions look like. And we'll see, especially in chapter 5, that they'll help you draw these phase planes by hand without technology. You don't have to do as well as the technology, but you can still get pretty good plots. Let me add these things in here, these nullclines. Let's see, where should we put it? Maybe after the stream plot here. I'm going to use contour plot to do it. Contour plot. F of xy equals 0. We'll plot the x nullcline. X goes from negative, I guess we're going negative 0.1 to 4 here. Same for y. Y goes from negative 0.1 to 4. And let's color it with contour style. How about green? See it? It's actually two lines. This line here and the y-axis. Does that make sense? If you look at the f of xy equation, here's the f of xy equation. If you factor in x out of that, that says one curve where it equals 0 is x equals 0, which is the y-axis. That's where x equals 0. If you think about this without one of the x's in there, you think of it as 3 minus 3/2 x minus 5y. I factored out the x. That's a linear equation in x and y. The graph is a straight line. It's evidently the other straight line that we saw. Along both of those, dx dt is 0, which makes perfect sense along the y-axis because we already knew that when x was 0, that x is non-existent. You only think about y. Y was as a logistic model. The vector field was pointing upward here, downward there, though we don't care about that part. This point was a sink along the y-axis. Along this line, take a look at these blue curves here, the stream plot. Those are crossing that green line in a vertical way. The tangent is vertical. How about a y Nullcline? Just change the f to a g and color it differently. Say brown. The y Nullcline consists of the x-axis where y is 0, and this line, solution curves are crossing that one horizontally. So when you know what those Nullclines are, they can help you draw this without technology even. Though we're not really at the point to get very skilled at that yet. Do notice where green and brown cross? Those are the equilibrium points. Here, green, brown. Here, green, brown. Here, green and brown. Where they're both equal to 0. Okay? That's my introduction to Nullclines. I was going to do it in other examples, but I think for the sake of time, we won't do it in class. I'll do it before I put it on Moodle like usual. Okay, now I would encourage you to look at these notebooks on Moodle. Friday's assignment as well is going to be just completion. So again, take more time to look at these things. I know these completion problems you had for today were kind of long. Hopefully the ones for Friday won't be quite as long. So there'll probably be more of them. Let's go on to the van der Pol equation. Again, I believe the original motivation for this was a certain kind of electric circuit. Okay? Though we could pretend, even if it's not realistic, that x is a position of a mass on a spring and y is the velocity. It's a nonlinear equation, actually, because of the nonlinear function right there. And that's not a constant, that's a function. Though in a sense I talked about pretending it was a constant. You can convert it to a first order system, which is also nonlinear. It's linear in this part, but it's nonlinear in this part. One thing I mentioned, we saw what the solutions look like here. Enter this here. And we also thought about Euler's method. I think my delta t needs to be smaller to do that here. Oh, I forgot to enter my Euler method function here. This, okay. There we see Euler's method. Let's try this. Why are we getting error? I'm not sure. Did I not, if I did my D solve, my ND solve, did I enter this one? I forgot. Oh, I'm not sure. Why are we getting error? Offhand here. It says it lies outside the range of data. Okay, now, evidently I didn't enter something. There's that solution curve, well, a solution curve for this particular initial condition. And I mentioned how it approaches the periodic solution. Why are we having troubles here? I think the problem's with Euler's method, actually. delta t smaller, and I think those errors go away. Okay. Different initial conditions still approach the same periodic solution. It's an attracting periodic solution, also called a limit cycle. And that's what we focused on last time. What I want to focus on, something different today, is that comment I made about how this x squared minus 1 kind of represents damping if x is large and anti-damping if x is small. Because it's positive if x is large and negative if x is small. That's kind of reflected in this picture by the fact that if you start out with an initial condition near 0, you get anti-damping. You don't get a damping of the oscillation, you get an increase in the amplitude of the oscillation. When you are far enough away from 0, that's where you get the damping. And what I want to emphasize here is that if we go really far away from 0, like maybe negative 100 to 100, both of these directions here, well, on this scale you can barely see that periodic solution. You really can't see it at all. I should probably get rid of those brown dots. And as far as you can tell, it's acting like a damped harmonic oscillator. Now we know when you get close to the origin there was that periodic solution, but you can't see it on the scale. So as far as you can tell on the scale, when x and y are real large, when the initial conditions are real large, it seems like it's a damped harmonic oscillator. That's the point I want to make. Okay? You want to think about these kinds of things as you read the book and as you work on the problems. These kinds of interpretations are important for helping you get an intuitive understanding of things. Something else I want to highlight is, what if we add a forcing function into this? For the right-hand side, for the original equation, the second order equation, this one, adding a forcing function, an external forcing function, effectively makes that 0 go away and makes it some function. Think about Newton's second law, F equals ma. In a sense, if you imagine the mass is 1, this is m times a there. And you can imagine putting this stuff on the other side, which if it were a harmonic oscillator or mass on a spring, that would be the term that comes from Hooke's law, and this would come from the damping. But we could also add some external force. With a mass on a spring, you could maybe hit it with a hammer. Every time it comes close to you, you can hit that mass with a hammer. That could be an example of an external force. A more realistic example of an external force could be the wind. If a bridge is kind of swaying up and down or back and forth, the wind could be some sort of external forcing. We could add an external forcing, and quite often, to keep things simple, you add a sinusoidal kind of wave here externally, maybe a sine function or a cosine function. And that effectively is what I'm doing here in the system. In the second equation, the dy dt equation, I'm adding an external force essentially. With period 2 pi over 5, based on the sine of 5t there, and an amplitude that I'm just calling a because I'm going to leave it unspecified. In the equations here, a is a parameter, and I'm making it a subscript of the right-hand side function, g there. We're getting close, aren't we? Okay. Enter those functions. I can still use MD-solve, keep the a in there. Things still depend on a. If I use Euler's method, I got to make the capital G function depend on a as well. What's going to happen in this picture? Well, initially I have a set at 0. So that's no external forcing, and the solution looks just like it did before. But what happens if I increase a now? Whoa! Is that right? Can that possibly be right? Doesn't that violate uniqueness? the solution curve is crossing itself? The answer is it does not violate uniqueness. And the essence of the reason is that you are looking at this picture in the wrong way, in the wrong space. The true graph of this parametric curve in the usual sense of a graph would include a t-axis coming out of the screen. And if you graph this in that space, you will see that it doesn't cross itself, and in fact no solution curves cross themselves or other solution curves if you add a t-axis in here. And we'll do that in a minute, but we're coming up to time moment here. 9:26:53. I'm ready to enter my Facebook post. What should we do for 20 seconds here? I guess we'll look to see if anybody responds to my Facebook post. I've been noticing people do not respond so much in the morning these days anymore. So we'll see. 48, 49, 50, 51, 52, 53. Yay, okay. All right, well, at the end of class, we'll see if anybody responded or liked it. Yeah, you're looking at this in the wrong space. It's crossing itself in the phase plane, but if we look at it in the right space, does this defy uniqueness? No, we're looking at it in the wrong space. If we put it in the right space by adding a third trivial differential equation to it, look at this differential equation. Tau prime equals 1. What is tau? Tau is the Greek version of t. Tau as a function of t will equal t. I made tau equal t by putting in this differential equation in here. That's going to add a third dimension to this to make the solution go into a third dimension. Let's see, I have to enter axes. I want the axes to be in here. Where did I put my axes? Enter in here. Oh no, where did I put my axes? This is going to make an error. Where did I put my axes in here? Okay, let's get rid of the axes here. This axes variable is supposed to represent axes, and I programmed it with parametric plot 3D before class, but I don't see where I put it, so let's just get rid of that. There's the solution curve in three-dimensional space when A is 0. You see the original picture if you look straight down like that. If we now let A increase, then we get our wiggly picture crossing itself, but in three-dimensional space it doesn't cross itself. Okay? So it does not defy uniqueness. Actually, if you think about this in a one-dimensional case, if you think about a non-autonomous equation in one dimension, you could, for example, get a sine wave as a solution. And on the phase line, if you drew the phase line for that, you'd have a point going up and down. And you'd be saying, does that violate uniqueness in that one-dimensional situation? And still the answer is no. Don't look at it in the phase plane, look at it in this extra dimension. But it does make non-autonomous equations more difficult to understand and analyze. In effect, what's happening here is the vector field is changing over time. Look at those vectors. The vector field itself is not constant, it's changing. The solution curve still needs to follow the vector field anytime it touches one of those vectors in the vector field at a moment in time. That's got to be the velocity vector if it were the right length at that moment in time. But because those vectors are changing, that's why you get the crazy behavior. Non-autonomous means it depends on time. Autonomous is independent of time. Oh, there's the axes. There, I put it here. I think you're going to skip the SUR model for the moment. And maybe we'll not do it today. Maybe do it on Friday instead. We'll see. I'll go ahead and enter the axes thing here. That has now stored a picture in the variable called axes. It's this picture right there to make the axes. I used parametric plot 3D with three simple parametric curves to create the axes. It'd be nice if there was some other way to do it. I actually could, let's see, make this a, what do you call it? An initialization cell, if I wanted to. And it would always get run every time I open this notebook. I'm not going to bother though. These are the equations that are the right-hand sides of the Lorenz equation, Lorenz system. It's a three-dimensional system. I should have typed it in here, but, well, it's dx dt equals sigma times y minus x. dy dt equals rho times x minus y minus x times z. And dz dt equals negative beta times z plus x times y. It's nonlinear because of that term and that term. But it's not far from linear. It's got three parameters, sigma, rho, and beta. In general, it's got three equilibrium points, although rho does need to be bigger than 1 and beta needs to be bigger than 0 to make these two real. Bifurcations are going to occur at rho equals 1 and beta equals 0 if I do allow rho to go less than 1 and beta to go less than 0 if I want to. Though evidently for Lorenz, when he was setting this up initially as a toy model of a weather system, they don't try to use this to predict the weather. It's not accurate for that. And what do x, y, and z mean anyway? It was a little toy weather system in a sense, a simplified version of a more complicated system. Yet it's still, even though it was so simple relatively speaking, it still exhibited quite interesting behavior, and that's what we're seeing. Using these solve to store solutions in this thing I called solution. And then we can look at those solutions in this space, and I made it nicer here, including the axes. There's the solution curve we saw. It is an attractor. If I change the initial conditions, technically I do change the solution curves, and this is an autonomous equation, so solution curves can't cross in the phase space either. In the phase space they can cross for non-autonomous, but not for autonomous. If I change the initial conditions, I'll get a different solution curve. However, the picture won't look much different. Change x, change y, change z. I am changing the initial condition, but the picture looks basically the same. No matter what initial condition I pick, the solution curve heads toward this funny looking thing, like a mask or something. Butterfly wings. Look at that thing. Isn't that cool? It's called an attractor. Okay? All solutions are approaching this strange looking attractor that I can't really describe in a ton of detail because it's very complicated as time goes by. It's very strange. In fact, it's called a strange attractor. That's the official name for it, a strange attractor. It's the Lorenz attractor, and the Lorenz attractor is an example of a strange attractor. What happens if you change the parameters, the rho, the sigma, and the beta? Well, it does change the attractor a bit, not much seemingly. Although if you change rho, watch this, it's going to go away. Look at that, the strange attractor went away to some other sort of less strange attractor. Oh wow, look at that. Bounce back and forth. See that? Bounce back and forth. Wow. Weird. Ultimately, the equilibrium points merge together at one equilibrium point at the origin when rho is 1. If rho is less than 1, there's only one equilibrium point at the origin. There's a bifurcation that occurs at 1. You can't see it, but there's now 3 equilibrium points there. Not acting too strangely at the moment. It gets stranger and stranger as rho gets bigger and bigger. It does exhibit what's called sensitive dependence on initial conditions. Now let me illustrate this by looking at the graphs of one of these functions. We've got x, y, and z. Let's see, we're going to make this two-dimensional, a regular plot. Let's get rid of the axes. Let's get rid of, what else? Well, we need to make this parametric plot 3D just a regular plot. I'm just going to plot x. So I'm going to get rid of y and z here. I'm going to plot x as a function of t in a tx plane, an ordinary kind of graph here. To do this, though, I think I need to put double square brackets and a 1 here. The reason I think I need to do that is so that it picks off the x coordinate of the solution. If I wanted to graph y, I'd put a 2 there. If I wanted to graph z, I'd put a 3 there. Putting double square brackets and 1, 2, or 3 picks off elements in a list in the order they occur. Plot range I better change, not 3-dimensional for one thing. And the horizontal axis is going to be time. I guess I'm letting b go, where's b? From 0 to 100. Did I do that with the ND solve? Yeah, I went up to 100. So I should go like 0 to 100 here. Negative 30 to 40 might be fine. Get rid of the z labeling the axes because there is no z axis here, and actually change this to an x and this to a t. I think this will work. Mathematics is changing where the origin is. There's x as a function of time. Very strange function. Probably never seen one like that in your life. You can make the origin stay where it should be by doing, I guess I don't even need the show, but let's just do axes, origin, 0, 0. That'll fix the moving origin. That will stay where it should be. If I change sigma, rho, and beta, I get different things. And again, if rho gets low, it's less interesting. If I change the initial conditions ever so slightly, oops, it affects the graph greatly. I mean, it's still just a general haphazard seeming pattern. However, the actual details of the pattern, in this case, low, high, small low area, high, low. The details of that pattern change drastically for even very small changes in these initial conditions. That's called sensitive dependence on initial conditions. Let me emphasize it in one more way. Let's see, some copy and paste magic here. I'm going to plot not only the original function here, but a second function. And this second function is going to be the same as the original, except one initial condition is going to be changed slightly. Instead of an x0, I'll make it an x0 plus 0.01. Make one of these solutions red, make one blue. Now I'm graphing two solutions. They're very, very close together in their initial conditions. Just x differs by 0.01. The graphs look the same for a while, but then all of a sudden, they're drastically different. And that's, amazingly enough, going to work no matter how close I pick the initial condition. Let me add a couple zeros in there. Same for a while, then they diverge again. Let me put a couple more zeros in there. Oh, how about 5 more zeros? 1, 2, 3, 4, 5. Same for a while, a little bit longer, but then they're different again. That's sensitive dependence on initial conditions. And the big lesson from this is, long-term weather prediction is basically impossible. That's what Lorenz concluded. This simple model is a toy weather system, and real-life weather is much more complicated.
the implications for weather prediction are you shouldn't try to predict the weather very far in advance. You're likely to be wrong. On the details, like what's the high temperature, whether it will rain or not. Climate, general things, it's warmer in the summer, colder in the winter, obviously you can say. But the detailed nature, you can't say so well. This leads to a phrase called the butterfly effect. Anybody ever heard of the butterfly effect? Few people? A butterfly flaps its wings in Mexico, causes a tornado in Minnesota 2 weeks later. And if the butterfly didn't flap its wing, then it's sunny. Is the butterfly effect real? Can butterflies cause tornadoes thousands of miles away a few weeks later in time? I don't know. The point is, it's possible. That's the point. There's a theoretical possibility of it. Okay. If you watch the old Jurassic Park, the first one, they talk about the butterfly effect a bit, chaos. There's a spot in the movie when they talk about that, if you're interested. All right. Linear systems and the linearity principle. This is the start of chapter 3, and that's what your main completion assignment is about for Friday. A linear system has the form dx dt equals some constant a times x plus another constant b times y. Do not include a constant term. I mentioned this the other day, either Monday or last Friday, that in this class and in linear algebra, with linear systems, you do not want to include constant terms. They're related to linear systems in a simple way, but they're not linear in the sense we want to focus on. Another word is often used, affine, A-F-F-I-N-E. Or fine, I think it's pronounced affine, but I might be wrong. That terminology is used if you include constant terms in this class. The dy dt equation has to look like that. So A, B, C, and D are constants. That's a system of two first order, first derivatives, scalar equations. We've actually already seen, we know we can write this as a system, or excuse me, as a single first order vector equation. If we let capital Y be a vector whose components are little x and little y, so that dy dt is a vector whose components are dx dt, d little y dt, assuming that's a valid thing to do. I guess I haven't said that that's valid, but that's the way we do it. That's how you take the derivative of a parametric curve, really. These things depend on t. If we let capital F of y, which you could also write as capital F of little x, little y, represent the right-hand sides of these equations thought of as a vector, this notation allows us to think of that system of two scalar equations as one vector equation. dy dt equals f of y. And it's autonomous because the right-hand side doesn't depend on t. Something new here in chapter 3, though, is to think of this vector field in a new way, to think of it as a matrix times a vector. Think of as a matrix, a 2 by 2 matrix, whose entries are A, B, C, and D, times a vector, a column vector, whose entries are x and y. What do you mean, think of it this way? To think of it this way, you have to know what it means to multiply a 2 by 2 matrix times a column vector like this. I'm saying the meaning of it is this. To multiply a 2 by 2 matrix times a 2 by 1 column vector, effectively you take the dot product of the first row with this column, which means take A times X plus B times Y, and that becomes the first component of the answer. And then take the second row of the matrix and take its dot product. I haven't talked about what dot products are, but many of you know. Take its dot product with this vector to get C times X plus D times Y and put it in the second entry of the vector. That's the answer. We're not going to think of it this way right now, but there's another way to think of this. Those who are in linear algebra know you can think of it in terms of what are called linear combinations of these columns. Not going to talk about that right now. Just realize that that's how this kind of product is defined. A 2 by 2 matrix times a 2 by 1 matrix, really, which is a column vector. Take the first row and this column. Take A times X plus B times Y, and that becomes the first entry, the first component of your answer. Take the second row here of the matrix, C times X plus D times Y. That becomes the second entry or second component of your answer. In Mathematica, dot products and matrix times vector products are done with periods. Matrices can be entered in two ways. You could do it as lists of lists, like this. That represents a matrix. If you want to see it's a matrix, you can do this. There's, you see, it can be displayed as a matrix.
Can you zoom in and just put
Yeah.
this?
Yep. Sure. All right. Thanks for letting me know. So you can enter it that way. You also can enter it with the basic math assistant. There's a matrix button right there. A equals, click the matrix button, go 1, 2, 3, 4. If you want to multiply A times a column vector that I'll call capital Y, you can put a column vector in there like this with this button. You can do it as A dot capital Y. The dot means matrix product. It can also be used for dot products of vectors. A period. There's the answer if you want to see it in matrix form. There it is. By the way, this slash matrix form is using matrix form as what's called a postfix operator. I can also put a matrix form in front of it. In the usual way and use square brackets. It's the same thing. All right. Why do we want to do this? Turns out to be a very good idea to do this. It will allow us to focus on the matrix A and its properties to help us understand the system of differential equations. We can do calculations just with the little a, little b, little c, little d to help us solve the system, to help us find nullclines, to help us find equilibrium points, to decide if there are infinitely many equilibrium points or not, to help us find the general solution. We're going to find what are called eigenvalues and eigenvectors, maybe starting a little bit on Friday, but continuing after spring break, to help us find the general solution of a system like this. But for the moment, we're just content with the fact that we write it that way. Let's take a particular example, though. And let's make it an example we know how to solve already, so it's got to be either fully decoupled or partially decoupled. Let's make it partially decoupled. X plus 2y,
3y are the right-hand sides. I can solve this. Y is going to be k2 e to the 3t, right? That's a y, that's why I'm calling it a k2 instead of k1. Plug that up there for y to help you solve for x. I don't have time, about 5 minutes here. That's a non-homogeneous linear equation. The corresponding homogeneous equation would be this. So x sub h would be k1 e to the t, right? X sub p is going to be some constant, call it a, e to the 3t. We've got to find xp prime. 3a e to the 3t. Think of this differential equation as a linear operator here, but the x on the other side. Meaning, plug the function into the left-hand side once the x is on the left side to see what function it spits out and figure out is there a value of capital A that'll make it equal that function. If you plug these things in, you'll get the 3a and a minus a. You'll get a 2a e to the 3t. We set this equal to 2k2 e to the 3t to help us see that a must equal k2. And that's okay, if we want that to be true for all t. Hopefully I haven't made a mistake. So the general solution of the x equation can be written as xh plus xp. That'll be k1 e to the t plus a is k2. So you get k2 e to the 3t. Hang with me here. Let's also solve the generic initial value problem. Well, actually, let's not. Let's leave it as a general solution here. The general solution of the original system can therefore be written as capital Y vector equals, vector's components are little x and little y. Little x is that, k1 e to the t plus k2 e to the 3t. The y is way over there, k2 e to the 3t. That is the general solution, or a general solution. It can also be written as this, with a little bit of trickery. Write it like that. Do you see how I got that? Effectively, first of all, I'm thinking of the terms involving e to the 3t as being separate from the term involving e to the t. And then when I look at this expression, then I write it as a sum of two vectors, k1 e to the t, 0 plus k2 e to the 3t, k2 e to the 3t. And then I factor out of those vectors a scalar quantity that allows me to write the vector as a constant. 1, 0 in this case, because if I multiply the scalar times this vector, times 1 times 0, I'll get this vector. And with this one, it's the same term in each case. If I factor that out as a scalar here, I get 1, 1. If I multiply the scalar through times each of these, I get that. This is the way we're typically going to write general solutions in this context. And the main thing to know as far as your homework due Friday is your book will often give you these answers and tell you to check that those solutions work. And you need to know that, knowing that you've got two solutions like this that are not multiples of each other, it's called linear independence, That's going to allow you to say that this general linear combination, where you have an arbitrary constant times that one plus another arbitrary constant times that one, is a general solution of the original system. So that's the kind of problem you're going to see a few times in your completion assignment due Friday. Okay? You're also going to see some information about determinants of like 2x2 matrices and how they reflect how many equilibrium points the system has. So that's the main thing I want to get across here. See you on Friday.